Right, so this video will focus on hybridization of atomic orbital. If you all remember, we studied that electrons live in orbitals inside an atom. So, what we had is that you had an atom with different shells. So, the guy in the center is the nucleus, which has positive and neutrons. So, proton and neutron, and then electrons are sitting around the shells. And we studied about quantum numbers. There are four quantum numbers that we care about right now, namely N, L, then you could write ML and MS, where this talks about the shell number, this talks about the subshell, and then we have orbitals, and then we have the spins. So what we studied using this is four, so if I write types of orbitals or subshells, you could have either S, P, D, F. And if you guys remember, S can have two suborbitals, P can, my bad, S can have one suborbital, P can have three suborbitals, D can have 5, and then F can have 17. And we just represent them with like boxes to denote how much space is there. These are 1, 2, 3, 4, 5. There's an extra one. And then similarly for D, you can have 7. 1, 2, 3, 4, 5, 6. And then we fill the electrons in this. But what happens is that when atoms, especially in covalent bonds, again, this does not happen in other bonds most of the time, but in covalent bonds, when atoms wanna combine or join, right, they will share electrons. That is one of the key features of covalent bonds, that they share electrons. That is the definition of covalent bonds. To enable that sharing, what you need is availability of electrons, right? Availability of electrons. So let's take an example. Let's take methane. Methane is CH4, right? And the way we draw the Lewis structure is that C is bonded with an H, 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 and then H, right? So what we say is that 4 electrons from C, 4 electrons from the carbon's outermost shell combine with the hydrogen's electron. Now, hydrogen only has one electron. So they each combine and then they create 4 bonds. Now these are 4 single bonds. Therefore, this is called as sigma bond. So this has 4 sigma bonds. But if we write down the the electronic configuration of carbon, so let's look at the carbon. The atomic number of carbon is 6. So let's draw the electronic configuration. 1s2, 2s2, 2p6. And then we can also draw the electrons out. So this should be 2p2. So 1, 2, 3, 4, and then 5, 6. So now you'll see here that these two electrons are paired. These two electrons are paired, but there is only availability of this little guy and this little guy. So in a way, there are only 2 electrons available to pair. But then we know that CH4 forms 4 bonds. So where do the 2 other electrons come from? So what happens, and we can even write hydrogen over here to showcase what is happening. hydrogen atomic number is 1. The electron configuration just becomes 1s1. You have this one guy. So this has one unpaired electron. I will write here this is available to bond. But then carbon only has 2 electrons. So how can one carbon form 4 bonds? For that purpose, what carbon does is something called hybridization and create hybridized atomic orbitals. So especially in this case, what happens is that the 2s2 and the 2p2 rearrange their electrons in such a way that there will be 4 unpaired electrons. So this electron jumps from here to the higher energy to come to a more stable state. So carbon, I can write it as hybrid. You can write this electronic configuration as 1s2, and then you could write it 2s1 and then 2p3. And if you draw it out, this is how it'll look like. So again, 1s still has the 2 electrons, but for the 2s, it has 1 electron now, and the other electron jumped from 2s to 2p, and it made 3 electrons here. So what we did is that we created here something called as hybrid orbitals. So these are hybrid orbitals. And because there are 4 hybrid orbitals that we created, giving us 4 electrons, or I should say 4 unpaired electrons, there was 1 s orbital involved and 3 p suborbitals involved, which are px, py, and pz. So you could write it here. This is px, this is py, and then pz. This hybridization is referred as sp3. So if I draw the energy diagram of this system, we had the 2s, then we had the 2p, 1, 2, 3. What we created is something in the middle of these two, right over here. So we created sp3, 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 and sp3. We created 4 sp3 orbitals. Each one of them had 1 electron. So earlier this had 2 and this had 2. So now, and this is sp3. So the energy lies in between these 2 atomic orbitals. Now these sp3, each one of them can combine with hydrogen. If you remember, hydrogen was nothing but 1s1, right? So it had 1 electron. So if you have 4 hydrogens, each of these can combine with an sp3 orbital in carbon, forming sigma bonds. Again, these are sigma or single bonds, and then single bonds. So you can have C, H, H, and then H, and then H. Sigma, 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 sigma. Or you could call it sp3, 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 and sp3. And this is how you create hybridization. So in the quiz, there was an example of silicon. Silicon has atomic number of 14. So if you write the electronic configuration, that becomes 1s2, 2s2, 2p6, 3s2, and then 3p2. Similar to carbon, this 3s or 3 shell has 3s and 3p2, and in 3s2 you have 2 electrons, but in 3p you have 2 electrons. And if I tell you that the silicon is forming a tetrahedral configuration or geometry, what this gives me, tetrahedral means 4 or 4-sided. So you have one silicon joined with other silicon, and then another silicon, and then another silicon, right? So here, if you carefully look, there is one sigma bond, the second sigma bond, the third sigma bond, and then the fourth sigma bond. So there are 4 sigma bonds, which are again also 4 single bonds. Now to form 4 single bonds, the central silicon needs 4 unpaired electrons, because paired electrons cannot combine with other electrons, so you need unpaired electrons to form these bonds. So just like carbon, what will happen here is that this 3s2 electron will jump to 3p orbital and will form sp3 hybridized orbitals. So if I write the electronic configuration again of silicon hybridized, the initial part would remain the same, 1s2, 2s2, 2p6, but after this 3s will become 1 and 3p will become 3, and if you draw it out, it will look like this: 1 electron in each of these orbitals. So now you have 1, 2, 3, 4. You have 4 unpaired electrons, and each one of this can combine with an unpaired electron in silicon. So you can have 4 silicon atoms, silicon, and you can build connections with 4 silicon atoms, because now you have 4 unpaired electrons. And again, just by carefully analyzing, you had 1 s orbital involved and 1 or 3 p orbitals involved, right? So this again can be referred as sp3 hybridization. It is not pp hybridization, it is not ss hybridization, it is an sp3 hybridization. Yes. Why? Because there is 1s and 3p orbitals involved. And then similarly, if you want to talk about something like ethene, that's also a common organic molecule that we study about. Formula C2H4. What you have is C double bond C, H, 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 and then H. And this here, instead of having, so you have sigma bond, sigma bond, sigma bond, sigma bond. Out of the double bonds that the 2 carbons are making, only one of them is sigma, and the other bond is a pi bond. And for pi bonds, no hybridization needed. So if you look at this carbon has 3 sigma bonds, which again corresponds to 3 single bonds. So now it will have 1 s orbital and 2 p orbitals involved. And this will give rise to sp2 hybridization. And then similarly, when you have carbon triple bonded with carbon, this gives you sp hybridization.